Imagine the solar system at twilight. The planets like porch lights in a quiet cul-de-sac, and the sun an old, reliable street lamp humming at the center. It is peaceful in a cosmic kind of way. Then, down the lane, a traveler appears. No change of address form, no forwarding information, just a long coat of frost and dust gleaming in starlight. That is our interstellar guest, 3IATLAS, easing toward the orbit of Mars, with the confidence of someone who has crossed more than one neighborhood and survived every speed bump. The red planet is up ahead like a brick house with a tidy lawn, and the visitor is reaching for the door knocker. Earth is basically a rock that won the cosmic lottery, which tonight pays out in curiosity instead of cash. And if you listen closely, you can hear the whole block scooting chairs to their windows. Something is gathering, and it is not a secret fleet. It is our attention, our instruments, and that wonderfully unruly human thing called imagination. Good evening, curious minds. Science doesn't need to shout to be fascinating. Sometimes it's best enjoyed the way you'd enjoy a late-night conversation, quietly, with a cup of tea, and maybe the soft hum of a fan in the background. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing. No pressure, only if you enjoy these calm journeys through the universe. Now, let's begin. Let us set the scene. The quiet is not silence, not really. Space has its own background music. The hiss of charged particles in the solar wind, the faint whispers of dust, the regular tick of planets keeping time. Into this orchestra, our visitor threads a new theme. It does not move like the locals, those comets and asteroids that circle the sun like regulars at a breakfast diner. This one carries a different rhythm, a path written somewhere else, as if the sheet music was drafted under another star. It is the stranger in a story who arrives with a suitcase of untold pages. There is no reason to panic. We are not in a disaster movie. We are in a science documentary with a sense of humor. Black holes are the universe's way of saying delete browsing history permanently. Comets are the universe's way of leaving us sticky notes made of ice, dust, and memory. Mars, being Mars, does not do fireworks on command. It is more of a stoic host with a thin scarf of atmosphere and a gravel driveway of ancient craters. But even a reserved neighbor can stage a dramatic entrance. As 3IATLAS draws near, the red planet becomes a kind of spotlight, not because it shines brighter than the sun, but because it sits at the right place at the right moment. The geometry of the neighborhood turns into a theater. Spacecraft that have been looping around Mars, taking the long view of a desert world, will angle their lenses and spectrometers like paparazzi at a surprise premiere. Telescopes on Earth will lean into the night, and somewhere a backyard observer will step outside with a thermos, whispering to the cold, "It is go time." What exactly is gathering? First, patience. Space rewards the long game. You cannot rush a comet. You wait, you watch, you let the data pile up like postcards. Second, instruments. There is a quiet choreography happening from control rooms scattered across Earth and orbiters stationed like vigilant doorbell cameras around Mars. Radio dishes flex, detectors cool down, schedules shift. Someone jokes that we are preparing for a party where the guest may only nod through the window and keep walking. Third, imagination. This is the fuel that keeps the porch lights on. We wonder what the visitor will show us. A whisper of unfamiliar gases, a tail shape that bends in an unexpected way, a color we have not quite catalogued. Photosynthesis is plants' way of saying we invented solar panels first. Comets are space saying we invented freezer burn first and then turned it into a museum exhibit. The beauty of a knock at the door is the moment right before it opens, the heartbeat of possibility. That is where we are. Our solar system has received 2 interstellar visitors before, and each time we learn that the universe writes footnotes in the margins of our expectations. Now a third arrives, and Mars happens to be near the foyer. You can picture the red planet straightening the welcome mat, and dusting off the doorknob. Meanwhile, we, the nosy neighbors with telescopes, are peeking through the curtains, narrating like a neighborhood watch with PhDs and a penchant for coffee. Why should you care? Beyond the thrill of a rare sky event. Because visitors from away carry clues about places we cannot reach yet. They are messengers from the wider galaxy. And sometimes the envelope is sealed with ice that has slept longer than our species has walked upright. When sunlight warms that ice, a cloud forms around the traveler, a faint aura that tells a story in scent and shade. We will not dive into the recipes tonight. There will be time for that later. For now, feel the scale of it. A little body, a huge journey, and a moment where it brushes past a world we have turned into a laboratory. That is a story worth pulling up a chair for. And yes, there is humor here, because wonder and laughter are cousins. Our red neighbor is the strong silent type, the friend who does not talk much, but always shows up with the right tool. Our visitor is the chatterbox, shedding little notes of vapor that say, "Hello, I was built far away by forces you are still mapping, Earth." Ever the enthusiastic neighbor waves wildly and sets out snacks in the form of instruments tuned to catch every whisper. If planets had group chats, this would be an all-caps moment with tasteful GIFs. We are not just watching, we are participating, not by steering the traveler, but by shaping the questions we ask it. So consider this the porch light moment. The sky is dim, the street lamp hums, and footsteps tap closer on the cosmic sidewalk. The knock is not loud, but it is unmistakable. Something is gathering in space. Our desire to know, our readiness to listen, our habit of turning flickers of light into meaning. That is the true party assembling as 3IATLAS nears the red door. Stay with the story. Next time, we check the stranger's passport and learn what marks a traveler as truly interstellar, how path and pace betray an origin far beyond our cul-de-sac. Chapter 2, Stranger's Passport. What makes an interstellar visitor? If the solar system had border control, the first question would be simple. Are you just passing through, or do you live here? To scientists, that answer is written not in stamps, but in the curve of a path. Local comets and asteroids circle the sun on closed tracks, like runners on a stadium loop. An interstellar visitor draws an open curve, a swoop that never closes. Imagine tracing a long arc across a page and then lifting your pencil and never coming back to the starting point. That is the giveaway. A path that does not bind. A route that says this traveler came from far away and will not be staying for dessert. How do we know that curve is truly open? We measure again and again, night after night. Each pinpoint of light is logged with the care of a librarian, checking rare books. With enough precise positions, astronomers fit an orbit and ask a yes or no question. Does the sun have the grip to keep this object forever? For residents, the answer is yes. For a true outsider, the answer is no, not even close. The math happens behind the scenes, but the idea is easy. A bound path closes on itself and repeats. An unbound path is a one-time wave goodbye. Space has no welcome committee, only spreadsheets. Speed is the second line on the passport. Locals move fast, but their speeds make sense for bodies held in the sun's long reach. An interstellar visitor rolls into town with extra energy, like a cyclist who crests the hill without pedaling. Even far from the sun, where gravity's pull is faint, the outsider is still doing more than a casual glide. That leftover pace is the signature of a long journey that began under another star's influence. There are no speed limit signs in deep space, but physics is the traffic cop, and it can tell when someone did not get their momentum from around here. A natural follow-up is the detective's favorite question. Could it be a local body that got flung out by a close pass with a giant planet? In theory, yes. A heavy hitter can spike a small object to interstellar speeds, but the clues usually do not line up. A recently ejected local would carry the scars of a near miss, and its trajectory would point back to a suspiciously recent encounter. Instead, when we chart a true outsider, The line through space does not trace back to a planetary billiards game we just missed. It points from beyond the family fence. The velocity and direction fit the profile of a traveler whose life story began at a different star's nursery, not a last-minute punt from one of our own giants. There is also the matter of a one-time pass. Locals have patience. They loop, return, and wave again after years or centuries. An outsider crosses the inner system once, tips its hat, and fades into the dark for good. That single visit sets a countdown clock for science. Observatories scramble not because of drama, but because windows slam shut fast in astronomy. When the sunlit side of an interstellar object is brightest, we get our best look. When it recedes, the night swallows it without apology. You could call it cosmic drive-through service. Order quickly and check the bag before the car merges back onto the highway. How do we check the bag? First, with astrometry, pinpoint positions that nail the path. Second, with photometry, careful brightness measurements that reveal whether the object spins like a baton or tumbles like a tossed book. Third, when possible, with spectra that tease out what sunlight is bouncing off or what gases are whispering away. None of these steps alone screams outsider, but together they form a profile. The clincher remains the path and speed, the geometry that refuses to close. Think of the process like a multi-page form. The shape of the orbit is the big checkbox at the top, and everything else fills in the tiny lines below. Why are these strangers precious? Because they are time capsules from other star systems. Picture a snow globe built in a distant town, sealed and set aside before planets that were fully baked. Over ages, gravity nudged it out, and it drifted between stars in deep freeze. Then one day, it passes our sun. And for a brief season, we can watch it sparkle. Materials that have not been reheated by countless close approaches carry the flavors of their birthplace. That birthplace might have had a different mix of ice, dust, and rock, a different pace of building planetesimals, a different recipe altogether. Each visitor is a note from the wider galaxy saying, "Here is how we did it over there." There is also the diversity dividend. The more outsiders we log, the better we can map the range of ways planetary systems grow up. One visitor hints that some systems fling out chunks early and often. Another hints that long-lived disks can stockpile pristine ingredients in their fringes. Over time, these scattered hints stack into a picture of stellar neighborhoods, unlike our own. It is like visiting multiple bakeries and discovering that everyone makes bread, but the crust and crumb are wildly different. Tasting only your home loaf will convince you there is one correct recipe. Trying the galaxy's sampler tray is humbling in the best way. The passport check has a cultural twist too. These objects remind us that our solar system is not an island. The space between stars is not empty so much as sparsely furnished, and every so often, a piece of someone else's furniture drifts by and makes us rearrange our living room. That jolt is healthy. It keeps our models honest and our questions curious. Wonder thrives when reality hands us something we did not order and says, "Try this." Finally, there is the naming ritual, the ceremonial stamp. Once the orbit says outsider, beyond reasonable doubt, the object receives an interstellar number, a label that marks it as a member of a tiny club. The label is not a trophy. It is a signpost for future researchers. Decades from now, when this past is only a memory, the record will still tell scientists, here is one of the rare ones, a traveler from elsewhere, a data point that expanded the possible. So that is how the passport gets checked. An open curve that never closes, a speed that stays stubbornly high, a one-time wave, and a sprint to capture all we can before the lights dim. Next, we will step onto the red planet's front porch and see why that world, thin air and all, is a surprisingly perfect theater for this particular encounter. Chapter 3. A Red Planet. Welcome, Matt. Why Mars is the perfect theater. Picture a stage where the curtains never quite close and the lighting is always set to faint amber. That is Mars. It is a world that whispers rather than shouts, a place where silence has a texture and time moves with desert patience, which is exactly why it makes a perfect theater for a passing interstellar performer. Dramatic shows shine brightest against simple backdrops, and Mars has minimal scenery to distract from the cometary spectacle sliding in from the wings. Start with the air, or rather, the polite suggestion of air. Mars wears an atmosphere so thin it would be considered a rumor on Earth. That sparseness is a gift for observers. Fewer molecules means less smearing of light, and fewer weather tantrums to scatter the view. Imagine watching a movie through a window that has only the faintest mist on it. On Mars, clarity is not a rare lucky break. It is the default. When a visitor struts past the sky, orbiters and rovers get to record the moment through a lens that is more cathedral glass than fogged bathroom mirror. The planet's modest veil does not snarl the signal. It steps aside and lets the cosmic guest take center frame. Now consider the color palette. Mars paints with two brushes, red ground and pale sky. It is the minimalist of the solar system art scene. Because the landscape and air are so restrained, any extra light, any tail glow, or odd hue from a passing object stands out the way a neon sign would in a monastery. Cometary gas might whisper with subtle shades, and against Earth's boisterous blue, that whisper can get lost. On Mars, the same whisper is a headline. The stage is calm enough that even a small spotlight from the heavens reads like drama. But do not be fooled by the hush. Mars has a lot going on behind the scenes. The planet fields an entire ensemble of orbiters that sweep around it in measured arcs, each carrying cameras and sensors tuned for different jobs. Think of them as a ring of balcony seats, armed with binoculars and notebooks. They can capture the sky, the ground, and the whisper of charged particles sliding around the planet like silk around a wire. Down on the surface, rovers act as grounded stage managers. They do not chase comets, but they can look up. They can send home the kind of local weather report that says whether dust is dancing or dozing, whether the sky is clear enough for a cameo from a passing tail. When a rare performance arrives, the entire Martian orchestra can play on cue. Here is the twist. Mars is a desert that loves a dramatic dust flourish. Every so often, the planet breathes out a global haze, a slow-motion confetti storm that wraps the world. That might sound like a problem, but it is also a plot device. Dust is Mars's signature, and when a comet passes, scientists get to watch how that ever-present powder reacts to new light and new ions. Does the veil brighten slightly? Do delicate streaks appear near the terminator line at dusk? Even a non-event is a clue, and on a stage like this, subtleties are easy to spot. It is the cosmic equivalent of listening for a pin drop in a quiet hall. There is also the geometry of vantage points. Around Earth, so many telescopes and satellites are already juggling weather, city light, and an atmosphere that thinks in layers. Mars is simpler. Instruments can coordinate with fewer competing priorities. One orbiter can take long exposures of the sky. Another can measure how the thin air responds. And a third can map the surface glow to check whether stray particles are doing anything interesting at the edge of space. Meanwhile, rovers can place their cameras on the horizon and record a time lapse of the heavens. It is a multi-angle broadcast produced on a planet that behaves like a steady tripod. In theater, you want good acoustics. On Mars, the metaphorical acoustics are superb. The planet lacks a strong global magnetic shield, which means the interaction between sunlight, charged particles, and the upper atmosphere is barefaced. There is little to hide the way a passing glow nudges the environment. It is as if the walls of the concert hall were stripped down to reveal the strings and pulleys, letting you see exactly how the sound waves bounce. A visiting tale does not have to shout to be heard. A murmur might be enough. The calm Martian sky also works psychological magic. Our brains love contrast. A quiet scene intensifies the sense of occasion. Mars offers that calm by default. A faint plume becomes a page-turner. A single ray of unusual light becomes a cliffhanger. Even if the show is modest, the setting makes it feel profound. It is like spotting a lighthouse beam in an empty ocean night. You cannot look away because the canvas amplifies the brushstroke. Finally, there is the narrative value. Mars has become our familiar neighbor, the friend who sends postcards and occasional selfies. We know the rocks by name, the hills by nickname, the dust by habit. So when something new crosses that well-loved sky, we instantly sense the difference. The red planet becomes a measuring stick, a stable frame we can use to tell how strange, how bright, how swift the visitor really is. Theater is not only about performance, it is about context. A face you know well makes an unfamiliar mask more intriguing. So yes, the planet of quiet horizons is the perfect playhouse. Thin air for clean lines, global dust for contrast and character. An audience of orbiters and rovers ready to observe without blinking, and a calm backdrop that turns even gentle cometary gestures into compelling acts. When the curtain rises on this flyby, Mars will not hog the stage. It will do what the best theaters do, vanish into the experience so the story shines. Up next, we will choreograph the angles and timing that make this encounter possible. The backstage geometry that turns a passing traveler into a once-only scene worth watching. Chapter 4, The Geometry of a Chance. Paths, angles, and timing. Every great photograph is a product of where you stand, where the light falls, and how long you can keep the shutter open before your arms get tired. Space obeys the same rules, just with fewer tripods and more gravity. When an interstellar traveler threads the inner system, geometry decides the story we get to tell. Paths, angles, and timing are not background details. They are the script, the lighting design, and the director's notes all at once. Begin with the path. An interstellar object follows a wide-open arc that cuts across the sun's realm like a single brushstroke. That arc is not a random squiggle. It is set by the energy the traveler brings from far away, and by the nudge it receives as it swings through the sun's gravity. Picture a stone skipping a single time across a pond, not looping back for an encore. The exact tilt of that skip sets everything that follows. Which hemisphere of Mars will have the better view, whether Earth can watch comfortably at night, and how long the object spends at brightness levels that make instruments happy rather than grumpy. Now for the angles, the true divas of this show. There are three that matter most: the angle at the Sun, the angle at Mars, and the angle at Earth. The angle at the Sun decides where the tail points, because comet tails are like introverts at a party. They lean away from the loudest presence in the room. The angle at Mars sets how the visitor is lit from the viewpoint of orbiters and rovers. The angle at Earth chooses whether the show happens in a dark sky at a convenient hour or skulks close to the sun where telescopes must squint and observers must set alarms. Gravity is the universe's velvet rope, but illumination is the bouncer, deciding who gets a clear look. Lighting is trickier than it sounds. If the sun is directly behind the observer, you get a face-lit view that favors the solid core and the bright inner cloud. If the sun is off to the side, dust in the tail can flare like chalk catching a spotlight, making delicate structures pop. If the sun is almost in front of the observer, tiny grains can throw light forward in a way that turns faint haze into a surprising blaze. Forward scattering is nature's sneaky brightness booster, like a stage fog machine that accidentally makes the headliner look legendary. The catch is that these dramatic angles often place the object close to the sun in the sky, which can shorten the nightly window and force a choice between drama and convenience. Space loves a trade-off. It keeps us humble and caffeinated. Timing is the third pillar. The visitor does not keep theatre hours. It keeps celestial hours. There are windows when it climbs high enough above the horizon of Mars for a long look, and other windows when it dips low, flirting with the glare. There are stretches when Earth gets long, dark intervals to track subtle changes, and other stretches when the object lurks in morning or evening twilight, like a celebrity dodging paparazzi. Mission planners compose a schedule that looks like a Tetris board, exposures from one orbiter at a certain time, measurements from a second orbiter a little later, a surface time-lapse squeezed in when the sky is calm, and coordinated Earth-based observations to cross-check brightness. The choreography relies on precise predictions called ephemerides, which are updated constantly as new measurements refine the path. Early on, the corridor of uncertainty is a boulevard. Later, it narrows to a hallway. By the time of closest approach, it is a chalk line on the floor. Parallax adds a delicious bonus. Mars and Earth see the visitor from different seats in the cosmic theater. That separation lets scientists triangulate position and motion with uncanny precision, like depth perception for planets. Even small differences in apparent location help sharpen the path. And sharper paths mean better forecasts of when a tail ray might sweep across a field of view, or when a faint outburst might be caught from both worlds at once. It is the astronomical version of a two-camera setup, except the cameras are hundreds of millions of kilometers apart, and one of them occasionally takes selfies with rocks. Do not overlook shadows and silhouettes. On rare occasions, geometry conspires to place the visitor's fine structures against a star field dense enough to act like graph paper. As the comet drifts, tiny changes in the tail's shape are easier to measure because the background provides a crisp grid. In other alignments, the object passes near the glaring sun from our perspective, forcing observers to use specialized instruments that mask the solar disk and let the faint visitor peek through. That setup is like photographing a candle next to a stadium floodlight by cupping your hand to block the glare. When it works, the results can be exquisite. There is also the question of cadence, the rhythm of repeated looks. Geometry dictates not only what you can see, but how often you can see it. Long, uninterrupted stretches allow slow evolution to be tracked, revealing how jets of vapor turn on and off as the object spins. Short bursts favor catching sudden changes, a brief brightening, a twist in the tail, a new plume appearing as a fresh patch of surface meets sunlight. The best plans borrow from both. Patience for the long arc, agility for the surprises. Space may not take requests, but it rewards good timing. Finally, remember that geometry is not static. Every hour changes the angles by a little, and those small shifts accumulate into big differences in what the detectors record. A configuration that emphasizes the solid core on one night might emphasize the billowing tail the next. A path that keeps the object inconveniently near the sun early on can swing it higher into friendlier skies later. The cosmic camera rig is temporary, adjustable, and slightly mischievous. It gives us a handful of signature shots if we are ready, and then it folds up and leaves without cleaning the stage. So the geometry of this chance is not just celestial trivia. It is the reason we may glimpse fine structure in a tail one day and subtle color gradients another. It is why Mars and Earth will sometimes talk past each other, and other times sing in perfect harmony. Angles pick the scenes, timing sets the rhythm, the path writes the arc of the story. Next, we will turn from camera placement to content and look inside the traveler itself, where cold layers and buried ices wait for their close-up the moment sunlight cues the show. Chapter 5, Ice That Remembers, Anatomy of a Comet Core. If you could hold a comet nucleus in your hands, you would be cradling a time capsule that smells faintly like a chemistry set left in a freezer. It is not a polished snowball or a glassy gem. It is more like a dark, lumpy briquette, stitched together from ancient frost, dust, and organic tar, all pressed into a fragile loaf by gentle gravity. The surface is typically so dark, it absorbs most of the sunlight that touches it, which is funny for an object famous for shining. The glow comes later. First, there is this quiet, inky thing that looks like it has been brooding for billions of years. What is inside that brooding lump? Start with water frozen into ice, the base note of comet construction. Layered through that are ices that freeze at colder temperatures, like carbon dioxide and carbon monoxide, which prefer life in the deep freeze. There can be ammonia, methanol, and other small molecules tucked between grains of dust, as if the universe packed a pantry and then forgot it in the attic. Threaded through this mix are complex organics, the sticky brown stuff that forms when simple molecules are bathed in radiation for ages. It is the universe's kitchen backsplash, stained by time. This is why scientists call comets primitive, not because they are simple, but because they have not been cooked and stirred the way planets have. The architecture is not uniform. Imagine a loaf with pockets, veins, and crusts. Some regions are packed tighter, others are fluffier, and many parts carry voids where tiny caves of ice and gas wait for heat to rattle them awake. The average density is low, so low that you could mistake the whole nucleus for a pile of snow mixed with soot. That porosity is crucial. It means sunlight cannot just warm a smooth slab. It has to thread into a labyrinth of pores and grains. Heat crawls inward, and as it does, it sets off changes like a row of dominoes you cannot quite see, only infer from the way the object begins to breathe. That breath is the comet's calling card. Sunlight falls, the upper skin warms, and ices nearest the surface decide it is time to sublimate, passing straight from solid to gas. There is no puddle phase in a vacuum, just an escape into invisibility. Gas pushes out through the pores, sometimes dragging dust with it, and together they burst into space as jets. If the nucleus is spinning, those jets act like tiny thrusters, adding a wobble or a nudge that changes the rotation. Over hours and days, the pattern of jets can make the comet tumble like a half-awake cat, which is adorable from a distance and a nightmare for navigation if you're flying a spacecraft nearby. The surface does not stay textbook smooth. As gas exits, cliffs can crumble, pits can open, and crusts can seal over. You end up with a battered landscape of ledges, sinkholes, and boulder fields, all sculpted by a star that is too far to touch but close enough to whisper. Some pits may be skylights into cavities where trapped gas once gathered before breaking out. Other scars might mark places where volatile ices were exhausted, leaving behind a darker, tougher rind that resists sunlight a little longer. If the nucleus looks like a dragon's molar, that is because it has been chewing through seasons of heat and cold for a very long time. Here is where origin enters the story. Different ices wake at different temperatures. Carbon monoxide and carbon dioxide can stir far from the sun, while water needs more warmth. If a comet shows strong activity while still distant, that hints at a rich inventory of ultra-cold ices formed in a region that never saw much heat. If the first real breath comes only when the object draws closer, that suggests a different birth pantry. Ratios between gases, recorded with care, become signatures of the nursery where the nucleus was assembled. In that sense, comet chemistry is space's version of a perfume counter. One spritz tells you whether the bottle was mixed in a frosty back room or a milder boutique. And a practiced nose can pick out the top notes, the middle notes, and the long trailing scent. Texture matters too. Some cometary ice can trap other gases in its structure, like bubbles locked inside a frozen sponge. When that ice warms, it not only releases its own molecules, but also frees the guests it has been holding hostage. That makes for sudden puffs, outbursts that turn a steady trickle into a brief fanfare. The presence of trapped guests tells us about the pace at which the nucleus formed. Rapid freeze can encase many visitors. Slower freeze is pickier. Even the dust that tags along tells a tale. Because tiny minerals can record the temperatures and pressures of the disk where the comet's building blocks took shape. A few grains might show they were forged near a hot young star and then carried outward, proof that early solar systems are restless places with conveyor belts that shuffle materials from furnace to freezer. Over time, repeated heating can leave a crust of baked material that shields the deeper ices. Think of it as a thin armor of dehydrated dust and organics. That armor can crack when internal pressure builds, and when it does, a new vent opens, revealing fresh ice beneath. the comet's breath changes tone. Observers see this as a shift in gas mix, or as a new jet that was not there before. Because an interstellar visitor is a one-pass guest, we are often catching it early in this process, before layers have been reworked by many circuits around a star. That freshness is gold. It preserves the flavors of a birthplace that may have very different recipes than our own system's pantry. None of this is gentle for long. As the visitor swings near its closest approach to the sun, heating intensifies, more vents awaken, and the coma swells into a ghostly envelope that hides the core. At that point, the nucleus is both actor and stagehand, throwing out the props that will create the show we see from afar. The heart remains a modest black rock of frost and dust, but its influence grows as gases and grains pour outward to build the larger spectacle. So the anatomy lesson is this. A comet nucleus is a layered, porous archive, wired to respond to light with breath and motion. Sunlight is the key that opens the file. The outgassing is the script that tells where the file came from. If we read it well, we can infer the climate of distant birthplaces and the shuffling of ingredients in young planetary kitchens. Next up, we step from the heart to the halo and watch how that breath turns into a glowing coma and tales that paint stories across the dark. Chapter 6, Coma, Tale, and Drama. The glow that tells stories. From a distance, a comet looks like a smudge someone left on the universe's window. Move closer, though, and that smudge turns into theater lighting with a plot. The nucleus breathes. The airless stage fills with haze, and suddenly there is a halo and two distinct tales that behave like co-stars who refuse to read the same script. The beauty here is not just visual, it is diagnostic. The glow is a confession letter written in photons, and if we pass the colors and shapes, the comet tells us where it has been and what it is made of. Start with the coma, that soft halo that swells around the core when sunlight wakes buried ices. Gas streams outward, dragging tiny dust grains with it, and the space around the nucleus becomes a temporary atmosphere, a lot larger than the body that made it. The coma is not a uniform fog. It is a simmering stew with knots, jets, and fans that reveal where vents opened on the surface and how the object spins. Think of it as breath made visible. Fresh gas near the core is dense and bright, then it thins and dims as it flows outward, like steam that fades as it leaves a kettle. Why does it glow at all? Two reasons. Dust reflects sunlight, just as chalk dust glows in a sunbeam. Gas, on the other hand, lights up because sunlight kicks its electrons into excited states, and when those electrons calm down, they emit very specific colors. It is cosmic karaoke. Different molecules pick different songs, and our detectors hear the playlist. That is why color is more than decoration here. Color is vocabulary. Out of that halo spring, the twin tails, each with its own personality. The dust tail is the graceful one, made of tiny grains that were hauled off the surface and now drift like bright ash. Sunlight pushes on them gently, and the result is a curved sweep that points roughly away from the sun, but remembers the comet's motion, so it bends like a ribbon in a slow river. The ion tail is the drama queen. Its gas has been peeled of electrons by energetic light, and those charged particles get hustled straight downwind by the solar breeze. The ion tail tends to be narrow, straight, and sometimes striped with rays that look like claw marks. One tail shows where the object has been, the other points to where the star's wind is going. Together, they sketch the invisible weather of interplanetary space. Now, about the palette. Many comets wear a faint greenish coma. That is the signature of small carbon molecules lighting up when they are bathed in ultraviolet sunlight. It is not paint, and it is not alien slime. It is physics in a good mood. The ion tail often leans blue, thanks to charged carbon monoxide glowing brightly in that part of the spectrum. Sprinkle in neutral sodium, and you can get a filament of amber, a delicate third tail that only emerges when conditions are just right. In rare cases, even metallic vapors can add a whisper of color farther from the sun than you would expect, as if the comet opened a drawer that most comets keep locked. Brightness is its own mystery box. Some grains are the size of smoke particles and scatter light strongly at certain angles, turning a modest dust tail into a luminous banner when you view it just right. Larger grains glow more evenly but fall behind more slowly, thickening the curve of the dust stream. Gas, by contrast, responds to the mood of the solar wind. A quiet solar breeze gives you a clean, arrow-straight iron tail. A gusty, tangled breeze carves kinks and disconnections, sudden steps where the tail seems to snap and start anew. That snap is not the comet throwing a tantrum. It is the star changing tempo. Because our guest is interstellar, unusual hues would be especially intriguing. If the coma leaned uncommonly toward particular greens, it might hint at a nursery where small carbon molecules were abundant and shielded, preserving fragile species that local comets rarely carry in such strength. If the glow favored reds or oranges linked to organic fragments, that might suggest a birthplace where radiation in the disk processed simple ices into more complex cocktails before the object was flung into the cold. A stronger than usual blue in the ion tail could point to an inventory rich in carbon monoxide or nitrogen compounds, a sign that the building blocks formed in regions so cold that even the shyest molecules settle down to freeze. Unfamiliar ratios would be a fingerprint from another star's pantry. Structure speaks as loudly as color. Spiral fans in the inner coma can reveal a twirling nucleus with one or two active vents, like a slow rotating sprinkler painting space with vapor. Narrow stria in the dust tail can trace the release of grains of a specific size over a brief spell, telling us the comet had a moment when a crust cracked and a fresh pocket of ice was exposed. Rays in the ion tail can align with wrinkles in the solar wind, allowing us to read a weather report from sunlight itself. Taken together, these details turn a pretty picture into an archive. There is even information hiding in the dark. Regions of the coma that stay subdued can indicate quenching, where collisions between gas molecules steal the energy that would have produced light. That tells you the inner coma is thick, the way fog swallows the brightness of distant lamps. Dust that dims the light from one side of the core more than the other can betray a veil of larger grains shading the nucleus, which speaks to how forcefully the jets are lifting material and how long those grains survive before drifting away. If our traveler shows colors or patterns that do not match the usual chorus, that divergence is the headline. We would not be looking at a weird mood swing. We would be looking at a different origin story. Planet-forming disks across the galaxy vary in temperature, composition, and sunlight. A comet's glow is a postcard from that diversity. It says, "The chemistry class over there emphasized different chapters." All of this, by the way, is why astronomers chase comets with instruments that split light into rainbows and measure polarization, the tiny twist in light waves after they bounce off dust. Each measurement is a letter in the alphabet of the coma and tails. Put enough letters together and you spell birthplace. So when 3IATLAS unfurls its halo and paints the sky with 2 exclamation marks of tail, we will be reading, not just admiring. The scene is gorgeous, yes, but it is also legible. Up next, we take that legibility to the red world itself and ask a practical question with a romantic sheen. If even a thin whisper of this stardust brushes Mars, what, if anything, will the planet's sky do in reply? Chapter 7, Mars, Meet Stardust. Possible interactions with the atmosphere. Imagine Mars standing on its porch, feeling a faint tickle on the cheek. That is what a brush with cometary material would be like for a world whose air is more suggestion than substance. No deluge, no storm, just a delicate encounter between a drifting veil of tiny grains and a planet that specializes in understatement. The question is not whether boulders will rain down. They will not, but whether the smallest shavings of the visitor, or a whisper of its gas, might graze the upper layers and leave signatures that orbiters can bottle and label. Start with scale, because it keeps expectations honest. The coma around a comet looks vast, but its gases thin out quickly. For Mars to taste that vapor directly, geometry would need to line up so that the planet passes through a portion of the cloud that is both wide and dense enough to matter. Even then, we are talking about a touch, not a gulp, more like catching the scent of someone's cologne as they stroll by. Comet chemistry is space's version of a perfume counter, and Mars has a surprisingly good nose. Its upper atmosphere, tenuous and cold, reacts quickly to new arrivals. What slips in does not linger. It flashes a calling card and is gone. Dust is a different story, and it comes in a spectrum of personalities. The tiniest grains, nearly smoke-like, can ride the solar breeze and drift across paths with planets. Larger specks, sand-like and heavier, care less about the wind and more about their own momentum. If a thin stream of any of these grains intersects Mars, some fraction will meet the air at high speed. The interaction is a performance in 3 acts: entry, ablation, and afterglow. Entry turns kinetic energy into heat. Ablation strips molecules off the grains, leaving streaks of excited atoms and fragments. Afterglow is the faint light from that excitement dying away. Think fireworks, but the budget version, no bangs, just shy sparkles. You might need night vision to appreciate. Could those sparkles be visible from the ground? Possibly, but the smart money is on subtlety. Mars's air is so thin that even fast-moving grains only heat a small volume. If anything shines, it would likely be brief streaks at extreme altitude, closer to a whisper than a shout. A rover camera might catch them as faint, needle-thin lines against the night, especially if planners tell the rover where to look and when. Even a non-detection helps, because it tightens the limits on how many grains were actually there. Orbiters carry the real sniffer kits. One type of instrument separates incoming molecules by mass and charge, allowing it to tell the difference between native atmospheric gases and extras that arrived with the visitor. If a whiff of unfamiliar vapor sneaks in, say a boost in carbon monoxide, a pop of methane, or a trace of exotic organics, these instruments can flag the spike as out of character for a typical Martian day. Another class of sensors looks at ultraviolet and visible light, watching for emissions from excited atoms and simple molecules. A sudden blush in a particular color can betray the presence of a species that was not there an hour earlier. It is the planetary version of a smoke detector, except it listens for light instead of particulate. Even the way the upper atmosphere behaves can change for a moment. As grains ionize and gas fragments interact with sunlight, they can create tiny pockets of enhanced conductivity. Radio signals beamed from one orbiter to another through that region will warp by a hair, and scientists will read those warps like seismologists read squiggles on a drum. A few minutes of altered signal delay can map the thickness and altitude of the layer where newcomers mingled with the locals. If Mars had a weather report for space, this would be the teaser. Brief patchy ionization, likely at twilight, no umbrella required. There is also the possibility of a gentle meteor shower, but it would not resemble the grand shows we celebrate on Earth under dark skies. On Mars, a shower would be more of a whispering drizzle, specks tracing lines that die out before most human eyes could catch them. Orbiters with fast cameras could gather time series imagery to highlight streaks against the stars, then triangulate speeds and directions to learn whether the grains were released from the visitor days or weeks before. From those reconstructions, scientists can estimate the size distribution of the dust and how strongly sunlight had pushed on it during the journey. Each streak becomes a yardstick for forces we cannot feel directly. Dust does not only glow, it also charges. Tiny grains rubbing against plasma in the upper atmosphere can pick up electric charges and respond to the electric and magnetic fields that drape Mars. Because the planet lacks a robust global magnetic cocoon, localized patches of magnetism over ancient crust become playgrounds where charged particles spiral and collide. A trickle of fresh ions could briefly enhance faint auroral glows that hug those patches, a phenomenon already known to show up when the solar wind gets feisty. A cometary contribution would be a quieter cousin to those displays. brief and subtle, but measurable by instruments tuned to the right wavelengths. Imagine delicate curtains of light stitched along invisible seams in the sky, there and gone in the time it takes to say, "Did you see that?" What about consequences at the surface? Almost none from a gentle brush. The majority of grains that survive to lower altitudes would be extraordinarily small and distribute themselves over vast areas. The planet's own ever-present dust would drown their contribution like a stadium crowd, swallowing a whisper. The romance here lives aloft, in the realm where molecules collide so rarely that outsiders leave crisp fingerprints before fading. Timing matters because Mars is a place of routine. Scientists know the typical daily rhythm of its upper air, how temperatures rise and fall, how the ionized layer grows and shrinks, how night glow flickers as atoms recombine. Against that baseline, even a modest cometary nudge stands out like a cymbal tap in a quiet bar. Orbiter teams plan their observations around these rhythms, targeting windows when the sky is usually calm so that any disturbance reads as signal, not noise. A handful of carefully placed snapshots can catch a transient layer forming and dissolving, turning a brief visit into a set of measurements that will be discussed long after the traveler has slipped back into darkness. So yes, a graze is plausible, and if it happens, the planet is ready to notice. Mars may be the strong silent type, but it keeps excellent records. A few extra molecules, a sprinkling of glowing specks, a ripple in the radio path. These are the souvenirs a passing visitor might leave behind. Small gifts, perhaps, but just enough to show that even a world with barely their air can be an attentive host. Next, we trade faint whispers for the unseen orchestra and listen to how charged particles and solar wind might conduct a more electric conversation in the planet's wake. Chapter 8, Weather Report for a Planet Without Much Weather. Martian Sky Effects. Welcome to the forecast desk, where the anchor is a robot. The green screen is the entire horizon, and the chance of rain is mostly a philosophical question. Mars is famous for doing very little with great consistency. That is precisely why any change, even a barely there shimmer, counts as headline news. When an interstellar traveler glides past, what might the Martian sky do? The honest answer ranges from a shy wink to a dignified nothing, and both extremes are valuable. Sometimes the universe hands you fireworks. Sometimes it hands you a ruler and says, "Measure carefully." Let us start with the most cinematic possibility, fleeting streaks. Picture the Martian night as a matte red canvas fading to ink. Against that, a thread of light sketches itself in less time than it takes to whisper, "Wow." These streaks would be drawn by tiny grains that collide with the upper air and warm just enough to glow before the thin atmosphere lets them slip away. They would be narrower than their cousins on Earth and higher, like handwriting on the ceiling, rather than on the wall. A rover might catch one if its camera is pointed right and the night is steady. Orbiters could have better luck, using long sequences to stack brief flashes into detectable lines. It would not be a show for the casual eye. It would be a show for patience and playback. Next on the subtle spectrum is air glow, a gentle radiance that hangs in the upper sky when atoms and molecules, tugged by sunlight during the day, calm down and release stored energy after dark. On Mars, this glow is usually faint and polite. If a drizzle of fresh particles or a brief burst of exotic gases nudges that layer, the glow could brighten along an arc or flare in patches near the edge of night. Think of it like someone quietly turning up a nightlight. No trumpets, no applause, just a measurable lift in a specific hue. For a world that treats understatement as a hobby, that is practically a parade. There is also the possibility of moving ripples, delicate waves crossing the sky, as the upper air responds to small jolts. Mars does not have convention in the Weather Channel sense, but it does have tides and waves driven by day and night cycles and terrain. A cometary nudge might seed new ripples or sharpen existing ones. To the eye, that would look like faint bands sliding past the stars. To an orbiter sensor, It would read as rhythmic changes in density or brightness, a heartbeat traced in light. Mars may not do cloud drama, but it can hum. Of course, the most likely headline is the one that never trends. No visible change at all. The visitor sails by. Instruments listen intently, and the sky remains its usual quiet self. This sounds disappointing, until you remember that science loves boundaries. A non-event does not mean ignorance. It means the universe has drawn a line and invited us to label it. If cameras see nothing above a known brightness, and spectrometers hear nothing above a known whisper, those limits become guardrails for every model. We can say with confidence how few grains cross paths, how weak any added glow must have been, and how quickly the upper air returned to routine. That is not romantic, but it is powerful. Earth is basically a rock that won the cosmic lottery. Science is basically the habit of cashing every receipt. How do we prepare to catch something that might not show up? By building a forecast plan with layers. Surface images can run time lapses in the hours when the sky is typically calm. Then compare those sequences to their own archives from similar seasons. If a line appears, they check its speed and slope against star trails and known satellites to rule out imposters. Orbiters can schedule coordinated looks, one mapping the faint glow near the evening edge, another sniffing the thin air for telltale emissions, a third relaying radio signals through the upper layers to catch any tiny shifts in density. The trick is consistency. You want the same angles, the same exposures, the same cadence many times over, so that any deviation stands out like a coffee ring on a clean desk. Even ground truth has a role. Dust monitors on rovers can report whether local haze is low enough to keep the sky transparent. If dust builds, streaks get masked. If dust settles, the sky becomes a better canvas. That simple context turns a maybe into a clear yes or no. Meanwhile, star trackers aboard orbiters act as accidental meteor detectors, logging any unexpected flashes as they maintain precise pointing. They were built to keep spacecraft steady, but they moonlight as night watch. Suppose the verdict is a handful of tiny streaks on 2 nights, and nothing on the third. That pattern is a story. It might say the stream of grains was uneven, or that the geometry shifted just enough to move the intersection point higher or lower. Suppose the verdict is a mild lift in airglow right after sunset, then a normal baseline. That is another story. It suggests a brief infusion of energy or fresh molecules that the sky processed and filed. And if the verdict is a clean, flat line everywhere, that still tightens our grip on the scene. The absence of a ripple can tell you the size of the pebble you did not throw. Why does this matter? Because Mars is a metronome. Its sky keeps reliable time. When something taps that rhythm, even softly, we learn how delicate systems respond to surprise. Those lessons apply far beyond this one pass. They inform how we interpret other transient events, how we design future instruments, and how we separate real sky quirks from instrument quirks. In other words, the short-term weather report becomes a long-term manual. And yes, there is room for a grin. A planet with almost no weather becomes the universe's most dependable meteorologist. Mostly clear, slight chance of whispers. Photosynthesis is plants' way of saying we invented solar panels first. Mars's sky is thin air's way of saying minimalism never goes out of style. Whether we catch faint lines, a gentle blush, or dignified silence, we win either way. Data is data, and curiosity turns all outcomes into progress. Next, we lower the lights and listen for the deeper soundtrack. How charged particles and the solar breeze might play the red planet like an unshielded instrument, composing a piece you cannot see, but you can definitely measure. Chapter 9. The Solar Wind Orchestra. Plasma games in the red planet's wake. If space had a house band, the solar wind would be the drummer, steady, energetic, and occasionally louder than anyone asked for. This stream of charged particles flows outward from the sun in all directions, carrying with it invisible magnetic strings. Most planets bring a big magnetic bubble to the concert, a private sound booth that keeps the drummer from rattling the furniture. Mars shows up without one. No global shield, no booth, just a thin atmosphere and some patchy crustal magnets, like small speakers scattered on the floor. That makes the red planet a perfect venue to hear the music roar. And when an interstellar visitor wafts a little ionized gas through the scene, the rhythm gets interesting. Here is the opening act. The solar wind races past Mars and meets resistance in the form of the planet's upper air. The charged particles cannot plow straight through dense gas without reacting, so a shock front forms upstream, a bit like a bow wave in front of a fast boat. Behind that wave, the wind slows and the magnetic strings drape around the planet, stretching and wrapping like ribbons in a breeze. Because Mars does not have a strong global magnetic shell of its own, those ribbons touch the upper atmosphere directly. Electric fields appear where the flow bends, and those fields can fling local atoms into space. In other words, the drummer is not just noisy. The drummer rearranges the furniture. Now add our visitor's contribution. The comet's breath includes molecules that can be stripped of electrons by sunlight or by collisions in the upper atmosphere. Once ionized, these newborn charges feel the electric fields wrapped around Mars and the push of the solar wind. They are like tiny kites suddenly tethered to moving strings. The wind picks them up, and in that pickup, it loads itself with extra mass. Mass loading may sound like gym talk, but here it means the flow slows and the magnetic ribbons sag. The shape of the wake behind Mars changes, the bow wave shifts, and the entire arrangement of currents and fields retunes itself. A little extra gas can change the tempo of a very large orchestra. Where do those newborn ions go? Many are swept into the tail that streams behind Mars, a long, invisible plume where magnetic lines guide charged particles away from the planet. Think of it as the venue's backstage hallway. With fresh cometary ions in the mix, the hallway becomes more crowded and the traffic pattern shifts. Some ions will collide with neutral atoms and swap charges, turning into fast neutral particles that fly straight without caring about magnetic strings. Those neutrals can escape or dive back, creating subtle energy signatures that orbiters can detect. It is a quiet form of tag: charged, neutral, charged again. The magnetic strings themselves have drama. When the solar wind is calm, draped lines behind Mars look smooth. When the wind gusts or changes direction, those lines kink, snap, and reconnect like rubber bands that have been stretched too far. Reconnection converts magnetic tension into particle energy, accelerating charges down the tail. Add a passing ion cloud from the visitor, and the reconnection site can migrate or intensify, because extra mass and extra charge change how easily the field lines twist and merge. You will not see fireworks. You will see rapid changes in particle counts and subtle flashes in specially tuned wavelengths, the plasma equivalent of a jazz drummer shifting from brushes to sticks mid-song. Mars's patchy crustal magnets add flavor too. They are not strong enough to build a full planetary shield, but they carve out pockets where the magnetic field is locally intense. As the solar wind slides past, these magnetic islands can deflect, trap, or focus charged particles. If comet ions wander into one of these zones, they can spiral and rain down, energizing the upper air in localized arcs. It is a spotlit solo rather than a stadium tour, but it leaves a trace that instruments can read. A small boost in specific emissions, a sudden change in electron energy, a tweak in the radio path between orbiters. Mars is basically a minimalist soundstage. Even a short riff is audible. Another player in this orchestra is turbulence. Behind Mars, the slowed wind and tangled fields create eddies where particles swirl and scatter. Introduce fresh, slower ions from sublimated gas, and you thicken the stew. Turbulence grows. The tail broadens. In some cases, sheets of current form and peel away. If the solar wind then surges, say after a coronal mass outburst from the sun, the combined system can experience brief disconnection events in the tail. where a whole swath of draped field lines snaps free and is carried downstream. That is the orchestra dropping to silence for a beat, then slamming back in on the next measure. Why does any of this matter for a flyby? Because plasma is nosy. It remembers who passed through, for how long, and with what mood. By measuring how the wind slowed, how the magnetic ribbons bent, and how many ions escaped, scientists can back out the amount and composition of the gas that entered the system. It is like deducing the size of a stone from the ripples it made in a pond. And because Mars has no global shield to hide behind, those ripples are clean. You are not trying to subtract the planet's magnetic roar to hear a whisper. You can hear the whisper directly. There is a practical payoff too. Understanding mass loading and tail dynamics helps explain how atmospheres change over time. Mars has been losing air to space for ages. Episodes that add ionized material, even tiny, temporary ones, teach us how quickly that loss can ramp up when the system is perturbed. They also show how energy from the wind couples into the upper atmosphere, a process relevant to any world that lives without a big magnetic umbrella. It is planet evolution through the lens of a jam session. And yes, it is fun to imagine the score. The solar wind lays down the beat. The magnetic strings provide harmony. Mars offers a dry, echoey room with a few quirky amps in the corners. The comet walks in and hands the band a new instrument for a night, a small one, but enough to shift the groove. You may not see the performance from the seats, but the microphones will capture every bar. When we play it back, we will not just hear a cool tune. We will hear how a planet without a shield negotiates with a star's restless breath, and how a passing traveler can change the conversation for a moment before the music returns to its steady, relentless time. Chapter 10. Observers Assemble. The Human Network. The signal goes out at twilight in one hemisphere, and before breakfast in another. Eyes up, lenses cooled, clocks synced. When a rare traveler threads the inner system, astronomy becomes a relay race where the baton is photons and the track wraps the entire planet. There is no single hero here. There is a chorus, a mesh of pros and hobbyists, robots and night owls, mountaintops and backyard patios, all humming the same tune. Catch every moment, from every angle, and share it fast. Start with the ground game. Professional observatories anchor the grid like lighthouses. On dry peaks where the air behaves, domes open, and mirrors breathe the night. Teams dial in exposures that shave the brightness just short of saturation, then push the faint structure until the noise complains. Each facility plays to its strengths. A big glass giant might chase the fine inner halo with surgical detail. A nimble mid-sized scope can patrol the broader tail and watch for sudden changes. Robotic telescopes sweep in cadence, scanning the predicted path so that no minute goes undocumented. It looks serene from the parking lot. Inside, it is a calm sprint, checkpointing stars, call-up flats and darks, confirm timestamps to the millisecond. In astronomy, punctuality is a superpower. Orbiting above the weather, space observatories join like the satellites of a film crew. One instrument splinters light into its rainbow to read chemistry. Another watches the sky near the glare, hunting structures that ground telescopes cannot touch. A third keeps vigil in wavelengths that never reach the surface at all. None of them can swivel on a whim. They live by carefully planned schedules and fuel budgets, so coordinators cue special sequences days in advance, inserting brief stares and slow scans between long-planned campaigns. When the moment hits, these eyes blink in choreographed turns, each handing off to the next, as Earth spins below. It is less like improvisation and more like ballet. Only the stage is everywhere, and the dancers wear solar panels. Meanwhile, Mars orbiters contribute their sidelong view, but the human network on Earth still shoulders the burden of immediacy. That is where amateurs, let us call them citizen astronomers, because amateur undersells their craft, change the game. They are the early warning system and the continuity plan. In suburbs and farm fields, On balconies and desert pullouts, small observatories wake. Some have mirrors the size of pizza pans, others the size of bicycle wheels. What they share is patience, skill, and a knack for ringing signal from stubborn skies. When a sudden brightening happens, it is often a backyard scope that sees it first, posts a measured alert, and prompts the big guns to pivot. How do thousands of people coordinate without stepping on each other? Through a web of message queues, mailing lists, and real-time channels where brevity is an art. A typical post is not prose. It is a compact field report: time, location, filter, exposure, result, uncertainty. Attach a small stack of images or numbers, and the hive mind gets to work. Others confirm or challenge, compare against their own frames, and fold the new data into updated predictions. It is the opposite of rumor culture. The fastest way to earn trust is to be precise about what you know and honest about what you do not. Then there are the rapid reduction pipelines, the unsung software heroes. As soon as a camera finishes a sequence, scripts snap to attention. They calibrate frames, subtract the instrument's quirks, align stars, and measure the target's brightness and position. If something deviates from the last hour's trend, if the glow swells, the tail kinks, or the nucleus flickers, an automated flag pings the network. It is like having 1,000 careful interns who never get bored and never spill coffee on the keyboard. The human eye still makes the final call, but the machines keep everyone honest and quick. Coverage, not just depth, is the secret sauce. The planet's time zones create a follow-the-night chain. As dawn chases observers off one continent, another team picks up the thread. Coastal haze ruining your evening, someone under a clear inland sky fills the gap. A thunderstorm parks over a major observatory. A rural backyard becomes the most important telescope in the world for 20 minutes. Astronomy loves giants, but it runs on redundancy. A single broken link can cost a discovery. 1,000 overlapping links turn chance into certainty. Even communication style matters. The best campaigns adopt a shared playbook before the show starts. Which filters to use on which nights? What exposure times keep stars crisp without losing faint halos? How often to switch to wide fields to catch the tail's reach? Having a common recipe means data can be stitched across instruments without the statistical equivalent of duct tape. You can feel the professionalism in the way volunteers mirror the standards of the big facilities. Labels are clear. Logs are meticulous. Calibrations are posted alongside images like nutrition facts on a cereal box. And then there is outreach, the heartbeat that keeps energy high. Live streams bring the hunt into living rooms. Short updates translate the arcane into the delightful. Here is the curve of brightness. Here is the time our robot friend will stare from orbit. Here is the best hour to step outside with a pair of humble binoculars. A well-timed joke, comets are basically space dandruff with excellent lighting, turns a chart into a memory. Viewers become contributors, reporting when clouds thin or when city lights shut off after midnight. The audience is not a crowd. It is a sensor network with enthusiasm. Of course, not every night delivers spectacle. Sometimes the headline is a neat, flat line. The network celebrates that too, because a quiet night validates models, tests pipelines, and strengthens trust. Confidence is cumulative. You build it by showing up, sharing clean data, and acknowledging the odd frame, where a satellite photobombs your perfect shot. In a field where nature writes the schedule, reliability is the rarest talent and the most contagious. So the call to assemble does more than fill folders with images. It rehearses the muscle memory we will need for the next surprise, and the one after that. The choreography of ground and space, the cadence of reports, the generosity of shared code and clean numbers. These are not side notes. They are the engine. When a traveler from far away slips between Sun and Mars, the human network becomes a single instrument, tuning itself in real time. The sky will do what it wants. We will be ready to listen together and to turn that listening into knowledge before the night rolls on. Chapter 11. What if it fragments? Drama we can learn from. Picture our visiting nucleus as a fragile suitcase that has been checked through too many airports. Most of the time, it trundles along intact, scuffed but holding together. Then one day the zipper gives way, and the contents tumble out in slow motion across the sky. For a comet, that unzip can happen for several reasons. Sunlight warms one side, and cold grips the other until stress cracks grow. Jets of gas act like thrusters and spin the body faster than it was built to bear. Or a pocket of buried volatile material vents suddenly, prying open a seam. Whatever the trigger, fragmentation turns a single actor into an ensemble cast. And while it sounds messy, it is also a gift. The universe sometimes opens the piñata for us. First, the mechanics. Comet nuclei are not granite boulders. Many are best described as loosely bound piles of grains and crusts, held together by gentle gravity and a patchwork of icy cements. Heat does not seep in evenly. It prowls through pores and fractures. As the day side warms, subsurface layers expand just a little while. The night side contracts. Over many cycles, hairline cracks can connect into highways. Meanwhile, jets of escaping gas push unevenly, adding a wobble or increasing the spin. At a certain point, the structure reaches its limit. A wedge breaks away, a cliff slumps, or the whole object splits into two or more pieces that drift apart, each now a tiny world with its own heartbeat. What follows is a transformation in what we can measure. Before a breakup, we see a blended personality, surface layers that have been baked and dusted by seasons in sunlight. After a breakup, brand new interior material is thrown into space and exposed. That is laboratory-grade freshness. Detectors can compare the glow from the freshly exposed gas to the older outer layers and ask, what is different? Does the interior carry more of the ultra-cold ices that wake far from the sun? Is the balance between lighter and heavier molecules shifted? Do the dust grains from the interior reflect light differently than the crusted grains that have been sunburned near the surface? Each contrast is a clue to how the nucleus was assembled when it was young. Brightness is the first obvious signature. A split often produces a rapid surge as sunlight hits a sudden increase in surface area and new vents open. Observers track how that surge rises and settles, because the shape of that curve reveals the size and number of fragments and how quickly the new vents choke or stabilize. Then comes choreography. The pieces drift apart at a glacial pace, their motion controlled by tiny pushes from continuing outgassing, as well as their mutual gravity. By measuring the separation over days, scientists can estimate the mass and density of the original body and test whether it was a single block or a cluster glued by frost. If the fragments rotate, the timing of their flicker lets us gauge their shapes. It is celestial forensics, and the crime scene helpfully repeats itself night after night. Dust behavior changes too. Freshly exposed layers often cough up a different grain size than weathered crust. Large, compact particles may dominate for a while, then give way to finer powder as vents erode. That shift alters the texture of the surrounding glow and the curve of the dust stream that trails the fragments. Analyze those textures carefully, and you can sketch a timeline of the breakup. First, the crust peeled, then the softer interior met daylight, then the vents settled into a new routine. Imagine reading growth rings on a tree that split itself in midair. There is also the tantalizing chance of discovering structure within. Suppose the nucleus was a contact binary, two lobes pressed together gently in deep time. A fracture may pry them apart, confirming that the original body was assembled from separate pieces. Suppose instead that the interior hides layers, like pastry. When one fragment loses a slab that reveals crisp strata, the changing rhythm of gas release tells us how those layers vary in composition or toughness. In a single week, we can learn more about strength and architecture than years of distant watching might reveal. Breakups are not only bonanzas for composition, they are also natural experiments in how momentum is exchanged in very low gravity. Jets that were once balanced on a whole nucleus now push on smaller bodies, altering spin states dramatically. Some fragments can tumble so that a morning vent becomes an afternoon vent within minutes. The resulting flicker in brightness is a coded message about torque and shape. Decode it, and you understand how sunlight and venting can sculpt small bodies over long spans. Decoding also explains why some comets survive multiple close passages, while others fail spectacularly. In other words, fragmentation is not just an event, it is a lesson in resilience. There are practical stakes too. A handful of new pieces means more sources of tiny debris, and that can matter for spacecraft that happen to be looking on. No one expects a hailstorm, but mission teams may adjust pointing or exposure plans to minimize the chance of a stray grain hitting a sensor. The same fragments, however, create opportunities. A smaller piece with a slow spin and a clean, fresh vent can be a more straightforward target for certain measurements than the parent body ever was. Sometimes the spin-off is the better interview. From a storytelling perspective, fragmentation rewrites the plot halfway through the chapter. A single arc becomes several, each with a different tempo. One child might fade quickly, exhausted by rapid venting. Another might steady itself and coast, its brightness leveling into a reliable beacon. A third might break again, revealing yet another layer of that original, complicated loaf. For scientists, each arc is a chance to test models with real, evolving data. For the rest of us, it is a reminder that even small worlds have dramatic inner lives. Comets are celestial granola bars, crunchy on the outside, surprises within. What about the long tail of consequences? Pun very much intended. Fragments often seed trails of debris that linger along the original path. Those trails can produce gentle showers when they encounter a planet years later, or they can simply thin into the wider dust of the inner system. Mapping how the fragments shed material tells us how quickly small bodies crumble under the constant nudge of sunlight and spin. In a galaxy full of fledgling planetary systems, that knowledge matters. It reveals how much raw material returns to the great recycling stream and how much survives to deliver water and organics to young worlds. So if our visitor unzips, do not mourn the mess. Celebrate the reveal. A breakup is not failure, it is disclosure. It turns a distant, enigmatic speck into a set of accessible questions with crisp, testable answers. The suitcase spills, the items scatter, and for a short, brilliant spell, we can read the tags on everything before the baggage carousel of space carries them away. Chapter 12. What if it swings by quietly? The science of boring. There is a secret that astronomers whisper with a smile. Quiet can be glorious. The sky does not always need confetti. Sometimes the best science arrives wearing slippers and speaking softly. If our interstellar visitor slips past Mars with low activity, no sudden brightening, no dramatic tail whiplash, that is not a dull night. That is a laboratory night. Calm turns the cosmos into a controlled experiment, and controlled experiments are where answers stop dodging questions. First, a subdued coma means cleaner measurements. When the halo of gas and dust is thin, the light from the nucleus is not drowned in its own exhaust. Photometric curves become crisp, letting us track how the brightness rises and falls as the body rotates. That rhythm reveals shape, not just size. A smooth, near-spherical object produces a modest, even pulse. An elongated or faceted body creates a stronger, uneven beat. With little haze to muddle the signal, even small changes stand out, and every wiggle in that curve is a clue to the geometry of the traveler's surface. It is like hearing the metronome behind the orchestra for the first time. Low activity is also a gift to spectroscopy. When gas release is sparse, the few species that do escape stand out like soloists on a quiet stage. Lines are narrower, blends are rarer, and faint signatures that would normally hide beneath bright cousins can be teased apart. If a trace molecule is missing, that absence can be stated with confident limits rather than shrugged away. Upper limits are not consolation prizes. They are fences that keep theories from wandering into fantasy. A gentle, orderly spectrum, let's chemists say, not just what is present, but how much of what is not. The dust, too, tells tales more clearly when there is less of it. Polarization, how light's orientation changes after bouncing off grains, becomes a sharp probe of particle size and texture when the path through the cloud is thin. With modest activity, scattered light is not scrambled by multiple bounces, so the polarization pattern reflects the true nature of the grains rather than a tangled average. From that, we can infer whether the dust is fluffy like frost or compact like soot, and whether grains are coated with organics or left bare. It is forensic glitter, best studied when it is not thrown by the handful. Dynamics love quiet nights as well. When outgassing is muted, the tiny rocket pushes that usually perturb a comet's path are minimized. Astrometry, precise position measurements, then pins the trajectory with extraordinary precision. That precision matters for an interstellar object, whose motion encodes where it came from and how the sun's gravity has nudged it. With non-gravitational forces reduced, the residual deviations from a pure gravitational track can be measured rather than guessed, and those deviations can be tied to specific weak jets or to none at all. In detective terms, low activity lowers the noise in the alibi. Thermal behavior steps into the spotlight too. A quiet surface means sunlight is warming a skin that is not being constantly excavated by jets. Infrared observations can then chart how heat flows and how fast the surface cools at dusk. That tells us about thermal inertia, the material's resistance to temperature change, which in turn hints at grain size, compaction, and a presence of crusts. If the skin holds heat well, the body may have tighter packing or a hardened rind. If it cools rapidly, porosity and fine powders may dominate. Either way, the thermal signature is not smeared by plumes of hot gas rushing past the thermometer. A soft-spoken comet also sets a baseline for everything that follows. The first two interstellar visitors taught us that outsiders can be quirky. To understand the range, we need the quiet end of the dial as much as the loud end. A well-characterized, low-activity pass becomes the comparison class that future objects must contend with. If the next one roars, we can say exactly how much louder. If it whispers, we can check whether the whispers match. Calibrated comparisons are how patterns become laws and how anecdotes grow up into evidence. Then there is the subtle psychology of discovery. A serene encounter forces patience. Without fireworks to chase, observers can devote time to long, uninterrupted sequences, hour after hour of rotation tracking, night after night of phase angle studies that reveal how the surface brightens as the viewing geometry changes. Phase curves drawn in peace are astonishingly informative. They decode surface roughness at millimeter scales and expose whether tiny frost patches brighten the dawn side differently from the dusk side. That level of nuance can go missing when the sky is busy. Even null results under calm conditions have muscle. Suppose sensitive instruments fail to detect certain volatile species at distances where they should awaken if the inventory were rich. That non-detection means the interior either lacks those ices or buries them deeply under insulating layers. Both possibilities inform origin stories. Similarly, if dust production remains below a tight threshold, we can infer that the surface is cohesive, perhaps armored by a crust that resists flaking. A quiet comet can be a tough comet, one that has learned to keep its secrets under lock and key. Knowing that is itself a secret unlocked. Quiet does not mean uninteresting for Mars either. A low-key pass still allows orbiters to test the plumbing, to confirm that their sensing of faint glows, rare ions, and tiny refractions is steady and reliable. Practice on a gentle case makes the next lively case easier to interpret. Think of it as a dress rehearsal where the orchestra perfects its tuning while the soloist hums a single note. You will thank the rehearsal when the concerto arrives, and yes, there is room for a wink. A placid comet is the cosmic equivalent of a cat that refuses to chase the laser dot. It sits, it stares, it teaches you patience. In return, you learn more about the cat than you ever did during the zoomies. The sky does not owe us drama, it owes us truth, and truth is often best heard when the volume is low. So, if 3IATLAS glides past with the poise of a librarian during story hour, celebrate. You will get cleaner light, tighter numbers, firmer limits, and a baseline that future visitors will either confirm or shatter. Either outcome is a win. Next, we step from silence back to the language of molecules, translating faint colors and delicate lines into postcards from a birthplace under another star. Chapter 13, Messages in the Molecules, Clues about Alien Birthplaces. If you want to know where a traveler grew up, do not ask for a selfie. Ask for a breath sample and a pocket full of crumbs. Comets oblige. When sunlight coaxes a whisper of gas from their skin and shakes loose a sprinkle of dust, the mixture becomes a biography in microscopic handwriting. Split the light, weigh the grains, and you can sketch a neighborhood the comet once called home. The universe writes postcards in vapor, and our job is to read the stamp and the smudge of perfume. Begin with the gases, the most talkative part of the message. Carbon monoxide and nitrogen compounds are the deep freeze crowd. They only settle down as ice in regions so cold and shaded that even a bold flashlight would give up. If our visitor exhales a generous portion of carbon monoxide far from the sun, that hints at a birth in the outer reaches of a star-forming disk. The kind of address where sunshine is a rumor and time moves slowly. Ammonia riding alongside strengthens the case because ammonia prefers frigid storage and does not tolerate warm hallways. Picture a pantry beyond the frost line, where ingredients gather like wallflowers and never sweat. Now add carbon dioxide, the diplomat between deep cold and mild chill. A strong showing of carbon dioxide, with only modest water vapor early on, implies that the raw building blocks were assembled where sunlight was weak but not absent, and where grains could mingle without melting into slush. Later, as the comet draws closer, water ice wakes and the balance shifts. The sequence matters. If carbon dioxide sings first and water hums later, we are hearing a childhood in the cold suburbs of a young star's city. If water belts out a tune early and loud, we might be dealing with a body that formed slightly inward or was warmed after birth and then shuffled outward by gravity's restless traffic. Methane and simple organics add flavor notes. A plume rich in methane suggests hydrogen-rich chemistry in a shielded nook of the disk, a place where radiation was tamed by thick blankets of dust. If we detect alcohols and more complex fragments, molecules that sound like they belong in a cautionary cooking show, that points to years of gentle processing, where slow radiation broke and remade bonds until flavors layered like a patient stew. Do we find a trace of oxygen-bearing organics without the expected companions? That could betray a period where ice mantles on grains were cooked by stray ultraviolet light, or mild shocks, rewriting the recipe without charring the pot. Dust carries the silent consonants that give structure to the sentence. Silicate minerals come in flavors that remember their ovens. Crystals like olivine and pyroxene require heat, not the blast furnace of a sun's face, but certainly a kiln compared with interstellar winter. If we find many well-ordered crystals mixed with very cold, loving ices, we are looking at a supply chain that once linked hot inner zones to frozen outskirts. Disks around young stars are not tidy. They are conveyor belts with detours. Grains can be forged near warmth, lofted by turbulence, and snowed outward into the cold, where they become seeds for comets. A crystal tucked inside a fluffy, porous grain is a ticket stub from that journey. Iron and sulfur-bearing grains, especially if they include compounds that form only under specific redox moods. Think of this as the chemical weather. Tell us whether the birthplace leaned toward oxidizing or reducing conditions. A reducing neighborhood, rich in hydrogen and stingy with oxygen, grows different minerals than one where oxygen struts freely. That mood shapes not only the rocks, but also the organics that glue onto them. Sticky, carbon-rich coatings hint at gentle assembly in calm eddies, while cleaner, sharper grains can betray harsher handling in crowded, turbulent lanes where collisions clipped off the fluff. Grain size and texture act like fonts in the postcard. Very fine, fluffy aggregates suggest that tiny particles met slowly and were never pressed hard, as if the nursery air was thick and the winds were tame. Larger, compact grains point to jostling and compaction, the signature of a region where gas churned and gravity tugged impatiently. If polarization measurements say the dust is wispy and highly porous, we are reading a line from a quiet backwater. If they say the dust is dense and reflective, the neighborhood probably hosted more traffic. Isotopes are the secret watermark the part counterfeiters hate. Ratios of heavy to light atoms, say, heavy hydrogen in water, or heavy nitrogen in nitrogen-bearing molecules, vary from one environment to another. A high fraction of heavy hydrogen whispers of ice that formed in bone-cold darkness where reactions crawl. Deviations in carbon or oxygen ratios can mark material that spent time near a star before being flung outward. These subtle numbers are not flashy, but they pin the postcard to a map better than any pretty stamp. What about the shape of the message through time? As a comet rotates, different vents open, and the mix of gases can swing like a playlist. If one side of the nucleus breathes more carbon monoxide and another gives more water, we may be seeing compositional layers from different eras of growth, or a quilted body stitched from several building blocks that met gently and fused. A truly interstellar object might carry patches from multiple neighborhoods in its original system. A little taste of the chilly outskirts here, a sprinkle of inner disk seasoning there. If it was assembled by slow collisions among migrants from different lanes, there is a bolder possibility: processed worlds. Suppose the object's dust includes minerals that need liquid water or sustained heating inside a parent body. That would hint that chunks of rock and ice once gathered into a larger ancestor with internal warmth from radioactive decay, then shattered. A piece of that rubble, wandering for ages, now passes our sun like a survivor with a complicated past. If we detect signatures of alteration, clays for instance, or iron minerals that swap forms only after bathing in water, that postcard does not read born in a cloud. It reads raised in a restless town, moved out, then evicted. Put it all together and the message gains nuance. A strong, early carbon monoxide melody, shy water, fluffy dust, and high, heavy hydrogen would paint a childhood in the outer disk shadows of another star, with conveyor belt delivery of a few warm, forged crystals, a louder water chorus, compact grains, and muted deep freeze species might place birth nearer to middling distances, followed by exile. An exotic mix with signs of altered minerals would argue for a past inside a larger body before breakup and escape. No single line decides the case, the whole paragraph does. This is why a flyby matters even if the show is brief. With each molecule logged and each grain analyzed, we turn a glowing smear into a map pin on a galactic blueprint. We learn whether planetary systems elsewhere shuffle ingredients the way ours did, or whether their kitchens stock different spices. And every time we decode one postcard in vapor, we get better at reading the next. Next, we bring that skill back home to a practical question. When fast movers sweep through the neighborhood, how does our coordination sharpen the guardrails for safety and readiness? The next chapter turns curiosity into rehearsal, and rehearsal into resilience. Chapter 14, Lessons for Planetary Defense. Practice under pressure. Call it a live fire drill with starlight. A fast mover slipping through the inner system gives us a chance to test every link in the planetary defense chain without the stress of an actual emergency. It is rehearsal with real photons. Instruments must wake on cue, models must tighten their laces, and analysts must turn fresh data into reliable guidance before the sky changes its mind. The visitor is not a threat. the clock is. And clocks are excellent teachers. First lesson, find it, keep it, and do not blink. Tracking a swift object is a game of precision timing. Observatories spread around the world learn to pass the baton cleanly, so the target never leaves the frame. When one site loses it to dawn, another is already locked on at dusk. This is not glamour, it is logistics. You practice pointing under wind, under thin cloud, under that annoying bright star nearby. You practice switching from wide field survey modes to narrow field, high detail modes in the time it takes to say now. Every clean handoff shaves uncertainty. Every sloppy one adds fog. Planetary defense loves clean. Second lesson, predictions are living things. When the first positions arrive, the orbit model is a sketch. With each new measurement, the sketch gains ink. The discipline is to update relentlessly. You do not fall in love with a previous forecast. You refine it or you drop it. Analysts learn to quantify what they do not know with the same enthusiasm they bring to what they do know. The uncertainty corridor narrows only if you feed it timely. Well-calibrated numbers. A rehearsal forces the rhythm. Observe, reduce, update, repeat. It looks simple on a diagram. In the dark, with real hardware and real weather, it is a craft. Third lesson, sensor fusion is power. A single kind of observation can mislead, blend them, and weaknesses cancel. Optical astrometry nails the where. Radar, if geometry allows, nails the how fast and how the object spins. Light curves hint at shape. Thermal data reveals how the surface handles heat. Even a modest flyby lets teams practice stitching these threads into one cloth. The payoff is a habit of cross-checking that becomes priceless when the stakes rise. It is the difference between acting on a rumor and acting on a report. Fourth lesson, classify quickly, but do not corner yourself. Is the body dust rich and fragile, or rock dense and tough? The answer changes how you would respond in a hypothetical hazard case. A fragile object turns to powder under atmospheric stress. A tough one keeps its nerve. During rehearsal, teams practice building fast provisional classifications from spectral fingerprints and brightness behavior, then tagging each with confidence levels. The trick is speed without bravado. You learn to say "we think," followed by how sure you are and what new data would move the needle. Fifth lesson, communication should be boring in the best way. No drama, no speculation, just clear updates that travel the world without mutating. A good alert reads the same in a desert outpost as it does in a busy city office. That means standardized formats, synchronized clocks, and language that is friendly to translation. It also means practicing when to speak and when to stay quiet. Too many updates bury the signal, too few invite confusion. Rehearsals with real events teach cadence better than any tabletop exercise ever could. Sixth lesson, automation is your teammate, not your boss. Scripts can calibrate images, flag anomalies, and push updates faster than any human can type. But humans decide when to trust a spike and when to question it. A rehearsal exposes brittle code, overconfident thresholds, and that one sneaky bug that always wakes up at 3 in the morning. You fix them now, while the only consequence is a missed plot twist, not a missed warning. Seventh lesson, practice the what-if branches. Even when no risk exists, you run the playbook. What if the path had crossed closer? What if the object were darker, or oddly shaped, or fragmenting? You simulate alternative realities using the actual observation cadence as scaffolding. This teaches teams how their tools behave under stress and where handoffs need smoothing. It is sports drills, but with ephemerides. Eighth lesson, decisions need thresholds written in daylight. A rehearsal is the time to test those thresholds. When would you widen the search field? When would you request radar time? When would you wake the people who hate being woken? Teams discover where their rules are too itchy or too sleepy and adjust. In a genuine crisis, you want no improvisation around the basics. Save creativity for the anomalies, not the checklists. Ninth lesson, hardware learns too. Cameras prove which exposure settings retain faint structure without drowning bright cores. Telescopes learn the mechanical quirks that appear only at certain sky positions. Antennas confirm that data pipes can handle a burst of uploads without stacking packets like dirty dishes. Repetition turns these quirks from traps into footnotes. The cosmos rewards muscle memory. 10th lesson, humility scales. Every rehearsal reveals a blind spot. Maybe a widely used model assumes a surface texture that the visitor politely disproves. Maybe a cherished pipeline mishandles very slow rotation and smears a light curve into nonsense. The win is not perfection. It is faster correction. A team that can say we were wrong by morning is a team that will be right by afternoon. In planetary defense, that humility is not a mood, it is infrastructure. And yes, there is room for levity. Training for rare dangers can feel heavy. A comet that minds its own business lets everyone stretch without gripping the armrests. You can joke that the universe is running a pop quiz with open notes. Earth is basically a rock that won the cosmic lottery. Planetary defense is the part where we learn to keep the ticket safe in a stiff wind. When the visitor departs, the scoreboard is not a single number. It is a binder of tiny victories, faster reductions, tighter orbits, sturdier code, cleaner alerts, and a team that trusts its rhythm. The next time a fast mover headlines the night, icy or rocky or stubbornly uncooperative, the practice you banked here will pay out in clarity and speed. Next, we will switch from tracking to touching and ask a deliciously ambitious question. Could we ever grab a sample from a passerby like this and bring a pinch of alien history home? Chapter 15. Could we grab a sample someday? The ambitious next time. Imagine telling a spacecraft, bring me a handful of yesterday from another star. That is the dream hidden inside every interstellar flyby. A visitor like this drifts through our yard, carrying specks that remember a birthplace we have never seen. If we could tag, taste, or even pocket a few crumbs without turning them into toast, the payoff would be outrageous. Chemistry bottled before planets finish their first arguments. Start with the gentlest option, the taste test. A fast probe could fly through the outer haze, sip the gas, and weigh the molecules on board. Think of a tiny laboratory that inhales and then whispers a list of ingredients. The engineering is sneaky, not flashy. The probe would need a scoop that admits only a controlled trickle, then a series of chambers that chill or warm the sample to tease apart different families of molecules. No one wants the sample cooked by the instrument meant to study it, so heaters must be precise, and surfaces must be cleaner than a surgeon's daydream. The benefit of an onboard tasting is immediacy. Numbers arrive while the glow is still in the rear window. Next level, the dust fly-through. The goal is to catch microscopic grains without shattering them into anonymous confetti. That requires a catcher that is both soft and strong, something that lets a fast grain burrow in and stop gently, like a diving board made of frozen smoke. The material has to be pure and predictable so that when we later analyze the grain, we know which atoms belong to the dust and which atoms belong to the catcher. Now picture the probe blazing along at interstellar visitor speeds with a catcher plate extended like a tongue. Space is stingy with brakes. The relative velocity is brutal. Shields ahead of the catcher take the first hits from larger particles, and the plate itself rides in a carefully chosen lane where the dust is sparse but not empty. Every millisecond matters. Bolder still, a rendezvous and tag. An interstellar object does not loiter. To sidle up to one, a spacecraft needs absurd hustle and even better timing. Solar electric propulsion could help by sipping sunlight and trading patience for speed. A gravity assist or two could twist the path into an intercept. Once nearby, the probe would fire a small dart or land a tiny package on the surface, grab a pinch, and bounce away. The choreography would look more like falconry than landing. The nucleus might be rotating slowly or tumbling wildly. The surface could be powdery in one patch and crusted in another. Navigation cameras would need to read shifting shadows and steer with the reflexes of a housefly. Autonomous decision-making stops being a buzzword and becomes the difference between success and an elegant miss. There is also the sprint mission. Launch on short notice, intercept on the first try, and bring something back in a capsule that survives the plunge through Earth's sky. The bottleneck here is not enthusiasm, it is readiness. You would want a mission design sitting on the shelf, modular enough that when a new interstellar target is found, engineers can swap in the correct trajectory and light the candle. Instruments must be pre-built, tested, and stored like carefully packed parachutes. The world would need a standing agreement for launch windows, tracking time, and a recovery team that can sprint into a desert or ocean and pluck a capsule the moment it lands. Every version of the plan is haunted by two goblins: contamination and heating. Contamination is the plot twist where your precious sample turns out to be part comet and part Earth breath. The fix is relentless cleanliness, from assembly rooms scrubbed of stray molecules to sample paths lined with materials that do not shed their own chemical opinions. Heating is the villain that erases memory. A grain that enters a collector at extreme speed can flash warm and rearrange its bonds. Designers fight this with shock-absorbing materials, layered shields, and sharp geometry so that any impact spreads out over distance and time. You also design the return capsule to keep a cool, stable ride through the blaze of homecoming, like a thermos bottle wearing a fireproof cloak. Why do all this? Because pristine crumbs are time travelers. Tiny minerals can record the temperature of their birth like tree rings. Trapped gases can carry the voice of a cold nursery that never saw a sunrise. Organic molecules, if sheltered well enough, can preserve how simple ingredients began to link into more complex ones. A single grain returned intact could show crystalline islands grown near a warm star embedded in fluffy ice from the deep freeze. A story you cannot write from spectra alone. It is the difference between hearing a song and reading the score. A cunning compromise is the two-stage mission. Do the taste test now and cache samples in deep space for a later pickup by a dedicated return craft. The first probe mounts the catcher, fills it during the fly-through, then stashes the sealed plate in a slow parking orbit around the sun. A second mission, not rushing at hyperbolic speed, comes along years later and reels in the cache at leisure. This splits the nightmare into two manageable dreams and lets the second mission fly a safer, slower course. Even ground truth matters. Back home, the samples would live in a facility that treats them like moon glass with stage fright. Cabinets would be filled with clean, inert gas. Tools would be made of materials that do not whisper stray molecules into the room. Every speck would be logged, sliced, scanned, and shared with a worldwide community that knows how to listen. Children not yet born would publish papers on grains caught by a probe that flew when their parents were still figuring out coffee. That is how long good samples work for you. It sounds audacious because it is, but audacity is how we turned lights in the sky into geology, chemistry, and history. The next traveler will not wait for us to get comfortable. If we want a pinch of another star's kitchen, we need plans on the shelf and teams that can move as soon as the universe knocks. And when we do bring those crumbs home, we will not just admire them, we will interrogate them kindly, asking them to tell us about worlds we may never visit. Next, we hand the microphone back to Mars itself and use the planet as an instrument, reading how its sky, dust, and invisible fields echo the traveler's passing, like a natural mirror with a memory. Chapter 16. The Red Planet as a Science Mirror. Using Mars to study the visitor, here is a trick the cosmos plays that feels almost like cheating. Sometimes the best instrument is a whole planet. Mars, with its lean air, dusty skin, and patchwork pockets of magnetic personality, doubles as a gigantic sensor suite. When a passing visitor breathes and sheds, the red world does not just watch, it reacts ever so slightly. Those reactions become a mirror held up to the comet's behavior. a second vantage point that does not live on Earth or in Earth's biases. If science is a conversation, Mars is the quiet friend who repeats what it heard back to you, slowly, so you catch the important words. Start with the sky, because Mars wears it lightly. High above the dunes and craters, the upper air is so thin that even small disturbances stand out. As the visitor's gases and dust drift through, the Martian sky behaves like photographic paper. A touch of charged particles and the paper darkens. A whisper of neutral molecules and the paper brightens in specific hues. Orbiters watch that subtle radiance night glow that rises and falls as atoms recombine. And they do it with clockwork discipline. If there is a brief lift in certain colors after sunset, it tells us not only that material arrived, but how quickly it mixed, how fast it fell, and how eager it was to give up its borrowed energy. That timeline, measured in minutes and hours rather than days, sketches the visitor's outgassing like the after-image of a sparkler traced across the darkness. Dust adds another layer to the mirror, and on Mars, dust is not shy. The planet's fine grains are always looking for excuses to dance. A passing stream of tiny particles can seed faint streaks or kindle ripples in the upper air that drift like tidal lines. When those patterns appear, orbiters catch them from above, while surface cameras at carefully chosen sites record the horizon below, creating a stereo diary. Match the timing and geometry, and you can extrapolate the density and speed of the grains that must have triggered the show. It is reverse choreography. Watch the footprints, reconstruct the dance. Now bring in the invisible scaffolding, fields, and currents. Mars lacks a global magnetic dome, but it does not lack drama. The solar wind drapes magnetic lines around the planet, and old crustal rocks hold local patches of magnetism, like ancient streetlights still humming. Introduce ionized gas from the comet, and that drape shifts. It is called mass loading, but you can think of it as adding weights to a hammock. The sag deepens, the pattern changes, and the flow slows. Magnetometers aboard orbiters feel those changes the way your ear feels, a change in air pressure. Small bends in the lines reveal how many newcomers were added and how they were accelerated. The planet becomes a sculptor's mold, revealing the shape and mood of the plasma that has just passed over it. Even radio links become part of the mirror. When spacecraft talk to each other or to Earth, their signals slice through the Martian ionized layers. If those layers are puffed up by new ions or thinned by rapid recombination, the conversation arrives slightly warped. Engineers who always know how their whispers should sound measure the difference and hand the distortion to scientists, who translate it into profiles of electron density at specific altitudes and times. That gives a vertical cross-section through the invisible action. Imagine a layered cake that briefly rises in the oven. These radio measurements tell us how high and how fast each layer lifted. Mars also offers a priceless geometry trick. Because the planet moves on a different track than Earth, it sees the visitor under different lighting and phase angles. One world might view a straight, narrow iron tail, while the other sees a fan where forward scattering makes dust grains blaze. Comparing the two is like moving a light around a sculpture to reveal texture. If the tail kinks or disconnects from Mars's perspective, but looks steady from ours, the culprit is not the comet alone. It is the solar wind's local weather. That split view lets us subtract the star's mood from the comet's habits, isolating the traveler's own rhythms. Timing turns the mirror into a metronome. Mars has a well-documented daily cycle in its upper atmosphere. Gentle expansions and contractions, tied to sunlight and nightfall, predictable as a heartbeat. Lay the comet's passing on top of that known rhythm, and any nudge stands out. A small delay in the usual evening glow hints at sluggish mixing. An early pulse suggests eager chemistry. Even a flat line, no change, narrows how much material could have been present without leaving a smudge. The lack of a footprint is still a footprint, crisp enough to rule out generous guesses and guide models back to humility. Surface sensors, humble and stubborn, close the loop. A rover's skyward camera can stare for hours, bracketing exposures to pull faint streaks out of the noise. Dust monitors can report whether the planet's own haze was quiet, so we know the stage was clear for any guest performance. Seismometers, surprisingly, lend a hand by logging pressure waves that creep along the ground when the upper air shifts. If a delicate pressure wiggle arrives right after the orbiter reports a brief glow high above, you have a stacked clue, sky and ground nodding at the same moment, both pointing at the visitor. What makes this whole arrangement special is that Mars is not an impartial vacuum. It has personality. That personality, once calibrated, becomes a yardstick. We do not only learn about the comet, we learn how a planet reacts to a prompt. In a galaxy of worlds without oversized magnetic umbrellas, that knowledge scales. It tells us how atmospheres erode, how energy couples into thin air, and how even small dust streams can paint temporary signatures on big canvases. Also, let us enjoy the narrative poetry. The Red Planet has been our field station for decades. Orbiters circling like patient owls, rovers inching along with cameras raised, antennas scribbling numbers into our inboxes. Now it serves as a faithful mirror, catching a traveler's reflection and sending it back with careful annotations. Mars is the universe's stoic neighbor who fills out incident reports with tidy handwriting. When the visitor moves on, the mirror remains. The data we gathered becomes a template for next time. Which instruments responded fastest? Which angles revealed the most? Which whispers in the radio told the clearest story? The planet has shown us how to listen better, and that sets the stage for our own species' other specialty, turning shared awe into culture. Next, we step out of the lab for a chapter on wonder itself, how a quiet flyby becomes art, jokes, late-night watch parties, and a refreshed sense that we live in a neighborhood worth staying up for. Chapter 17, Culture Shock in Space. Wonder, memes, and meaning. When a traveler from beyond our neighborhood glides past, something pleasantly human happens on the ground. Schedules bend, coffee becomes a food group. Windows that normally reflect living rooms at night turn into tiny observatories. A comet near Mars might be a physics problem to the instruments, but to us, it is an invitation. We answer with art, jokes, and a lot of standing in the dark together, pointing at the same patch of sky like we have rediscovered fireflies. The first wave is always chatter. Group texts light up with grainy photos and heartfelt advice, such as face northish. Social feeds fill with sketches, short poems, and blurry streaks labeled proudly as evidence. Someone designs a sticker that says, "I stayed up for space, and all I got was this glorious smudge." Someone else edits a lo-fi playlist called Dust and Quiet. The tone is cozy, not grand. You do not need a mountaintop. You need a warm jacket, a friend who will gasp on cue, and a horizon that does not argue with you. Then come the backyard makers. A high schooler prints a comet stencil and sprays biodegradable chalk across a bike path, leaving a glowing trail for morning joggers. A librarian hosts a midnight zine workshop called A Visitor Walks into a Solar System. In living rooms, children fold paper into improvised tales and hang them from floor lamps to stage their own nocturnal theater. Across town, a barista turns foam art into tiny comets and swears you can taste the difference between dust tail and ion tail, which is obviously nonsense and somehow still perfect. Humor becomes our second telescope. We roast the universe with love. We say Earth is basically a rock that won the cosmic lottery, then toast the luck with cocoa in mismatched mugs. We note that black holes delete browsing history permanently, which is comforting if you have ever searched for how to fix a squeaky fridge at 3 a.m. The jokes land because they keep the door open for people who do not speak spectrometer. Laughter is the caption that says you are welcome here. No prerequisites required. Artists do not ask permission. They just make photographers chase the faint glow above rooftops and stitch time into arcs. Painters translate the hush into oils that look like weather on a dream. Street musicians set up near late-night watches and play slow, patient songs that match the way the sky moves. A dancer in a community studio rehearses a piece called One Pass Only. Each gesture, a curve that never closes. None of it is official. All of it is documentation of a feeling that refuses to be filed under science alone. Teachers become ringmasters of wonder. Planetarium staff lure families with blanket forts under digital stars. A middle school science club builds cardboard spectroscopes from old discs and peels rainbows out of hallway lights, rehearsing for the rainbow that belongs to the real thing. A scout troop learns how to pronounce the visitor's name without stumbling, then promptly adopts a nickname anyway. The point is not precision. The point is ownership. This is our sky tonight, and we are allowed to engage with it. Night gathers its own rituals. Rooftops evolve into temporary commons where neighbors meet without small talk because the sky has already supplied the topic. Someone shares a thermos, someone shares a myth, someone teaches how to dark adapt your eyes and how to forgive your camera for being mortal. Pets wander through the scene, profoundly indifferent to cosmic heritage and profoundly helpful in keeping everyone warm. There is a quiet joy in realizing that looking up is a team sport. Of course, the internet does what it always does. It spawns memes at the speed of delight. A photo of a sleepy cat in a cardboard observatory becomes the mascot of the week. A looped animation of the comet sliding behind Mars gives the planet a magician's cape. Threads run with the prompt, if the comet could text, what would it say? And answers range from wish me luck to bring snacks. Do these jokes contain facts? Not many. Do they carry people into the room where facts live? Absolutely, meaning sneaks in the back door. A nurse on night shift steps outside between rounds and feels the quiet align something inside that has been noisy all week. A new parent rocks a baby under the faint glow and realizes that fatigue can coexist with awe. A retiree who once built model airplanes now tunes tracking motors on a homemade mount and whispers, still learning, we tell ourselves we are watching a comet. We are also watching ourselves behave well, patient, curious, sharing. There is a social gravity to these nights. City light policy earns a second look when people discover they can see more if a few bulbs take a break. Libraries extend hours because the line to borrow binoculars wraps the lobby. A community college schedules a talk titled How to Look Slowly and fills every seat. Wonder turns out to be civic. You can measure it by the number of strangers who become acquaintances because the sky gave them an excuse. Not every moment is profound. Someone drops a lens cap and spends 10 minutes searching by headlamp like a cautious raccoon. A cloud decides to cosplay as a tail and gets roasted by 3 blocks of amateur meteorologists. The comet itself is sometimes stubborn, refusing to brighten just when you brought the neighbors. That is fine. The sky does not take requests. It gives you a rehearsal for gratitude. Even the quiet nights add up, making your inner calendar less about deadlines and more about crescents, oppositions, and flybys that on paper are tiny, but in person feel oddly large. Maybe that is the real culture shock, realizing how easy it is to feel at home under something that will never know your name. We are small, yes, but calibrated small. The kind that fits well inside a universe that is generous with spectacle. If you budget for patience, when the visitor fades, the memes go stale, the playlists get retired, and the coffee machine finally rests. What remains is a memory that does not need sharpening. We stood together, we looked up, and the ordinary night agreed to be extraordinary for a while. Up next, we gather our notes, wipe the dew from the gear, and ask the inevitable closing question. After the curtain falls on this one-time performance, what do we actually carry forward into the next encounter? And what surprises might the next traveler pack in its suitcase? Chapter 18. Before the comet fades. What we carry forward. The show winds down the way good cosmic theater always does, not with a curtain drop, but with a long fade that leaves you blinking at the ordinary night. Our visitor glides on, the red world exhales, and the detectors cool. Yet the real ending is a beginning, because the notes we made while the lights were bright will shape how we listen next time. First, we leave with a sharper sense of how to tell an outsider from a local. The sky wrote its verdict in the shape of the path and the stubborn pace that refused to be tamed, and we learned to read it quickly. That skill is not just taxonomy, it is triage. The moment a new wanderer appears, we now know which tools to deploy, which angles to favor, and how fast to trade sketches for maps. The confidence did not come from a single image. It came from a disciplined cadence of measurements that turned a streak into a story. Second, we carry an improved appreciation for lighting and geometry. As co-authors of the plot, angles were not trivia, they were the script. Certain views favored the dusty veil, others exposed the straight blue hush of charged particles, and timing decided whether we got a gentle portrait or a sharp profile. We learned to accept trade-offs and to plan sequences that harvest different truths on different nights, like a photographer who knows the value of both dawn and dusk. Third, the anatomy lesson now lives under our skin. The core behaved like a memory box that releases secrets when warmed, and we listened as gas and grains translated that memory. We found that small shifts in color and a tilt in polarization can whisper about grain texture and buried ices without ever asking us to land. That is a portable insight. It means future outsiders can be profiled with finesse even when they keep their distance. Fourth, the red world proved itself again as more than scenery by watching the planet act as a sensor, its upper air brightening here, its radio pathways warping there. We discovered a second vantage point that did not depend on our own weather or our own biases. Mars reflected the visitor's mood in subtle echoes, and those echoes sharpened our models of how thin air negotiates with new arrivals. That knowledge scales to other lean atmospheres and other quiet worlds. Fifth, we learned that both drama and restraint teach well. If the traveler shed pieces, we saw fresh surfaces bloom and compared new breath to old crust. If it remained composed, we found the gift of clean lines and quiet baselines that locked down what was absent as firmly as what was present. Either way, the science moved forward. Spectacle is optional, rigor is not. Sixth, the molecules did what molecules do best. They gossiped. A particular balance of deep, chill ingredients against warmer-born companions hinted at neighborhoods far from our sun, places where disks shuffle materials like bustling markets. We did not just catalog names, we mapped childhoods. A tiny crystal nestled in fluff told us a conveyor belt once ferried warm-made grains into cold streets. A trace organic carried the scent of gentle processing rather than violence. The universe writes postcards in vapor, and now we recognize more stamps. Seventh, the network of watchers proved it can behave like a single instrument. Ground observatories, backyard scopes, space telescopes, and orbiters swapped the baton without dropping it. Software pipelines caught blips before they became rumors. Updates moved in plain language at a sensible pace. That choreography is not background. It is the backbone. Practice turned it from aspiration into muscle memory. Eighth, the rehearsal for readiness paid off. We tightened orbits, tested thresholds, and tuned alarms without the stress of a crisis. The playbook absorbed small corrections: when to widen the search field, when to request radar, when to pivot filters. We also exposed brittle assumptions and retired them. Humility traveled with the data, and that is perhaps the most practical souvenir of all. Ninth, the ambitious itch grew stronger. Fly-through samplers, soft catch materials, cache and retrieve strategies. These graduated from thought experiments to draft blueprints annotated with what we now know about grain sizes, jet rhythms, and workable approach lanes. The dream of bottling a pinch of alien antiquity feels less like a fantasy and more like a waiting room with a number in your hand. Twelfth culture did its quiet work. People who stood under the same sky will remember that they stood together. That matters, even in a document that celebrates spectra and vectors. Wonder is not extra. It is fuel. It keeps cameras pointed, code clean, and late nights friendly. What are the new questions we taped to the lab wall on the way out? Here are a few. How wide is the true diversity of outsider chemistry? And where do our samples sit in that spectrum? How often do these objects carry minerals forged near warmth into the cold? And what does that say about traffic patterns in infant systems? How do thin atmospheres respond to repeated brushes with small ion clouds? And could those brushes cumulatively sculpt escape over long eras? How early could a launch-on-demand sampler be ready? And what minimum payload still returns life-changing insight? Which community practices turned out to be essential, and which were ceremony masquerading as necessity? And then the bolder what-ifs. What if a future visitor arrives dark as fresh charcoal, daring us to find it with heat rather than reflected light? What if one is bright as frost and spins so fast it flickers like a lighthouse, exposing new vents every few minutes? What if a rocky outsider shows no breath at all, but carries minerals that only form inside larger bodies, telling us it is a shard of a world that once had warmth and then came apart? What if a giant planet in our system briefly corrals a passerby into a months-long loop, offering the luxury of time we have never had with such a guest? If this was visitor number 3, what story might number 4 tell? Maybe it brings a composition we have not yet seen, a palette that forces us to redraw our maps of other stars' kitchens. Maybe it sweeps a path that lets not just Mars, but another world act as a mirror, Venus with its bright veil, or a far-out giant with a magnetosphere that turns the plasma conversation into a symphony. Maybe it arrives when a shelf-ready sampler can meet it, and we stop guessing what the crumbs look like, because we can hold them up to the light. For now, the night returns to its usual tempo. We file images, archive spectra, and write code that will wake politely when the next alert appears. The lesson is simple and not at all small. The universe will keep sending chances. Our job is to stay curious and be ready. Visitor number 4 is out there somewhere, rehearsing an even stranger story. When it knocks, we will know which lights to switch on